Hello. Yes, thank you. Am I on?
Yeah.
I'm on. Okay. What time is that? Yeah, I'm sorry, I'm late. A couple minutes late. All right. I'll leave the door open. There might conceivably be people from. Okay, so we're setting up. This may be the last lecture on just the general setting up of this stuff, giving kind of an overview of the principle of functoriality and where it leads. So we talked about what the principle of functoriality says. We talked about L functions, how you would define L functions for general automorphic representations. I do need to take a slight generalization. We took G to be a split group. We took G over Q. This is before, this was last time. Split. And that's the simplest situation. One can really think of just G being GLN and everything that gives an idea of everything that's happening. But more happens, more stuff happens. First of all, it's better to take F to be an arbitrary number field. And G to be quasi-split. Quasi-split, the definition of quasi-split is that the group G has a Borel subgroup, which is a maximal solvable subgroup. Any reductive group G has a Borel subgroup. It's just that it's not necessarily going to be defined over the ground field. If the ground field's algebraically closed, it always has a Borel subgroup defined over it. G quasi-split means that G has a Borel subgroup which is defined over F. And quasi-split groups there's a very nice way to construct them from split groups. I mentioned split groups, yes. One definition of quasi-split is that it has a Borel subgroup, which is a maximal solvable subgroup within the group of complex points. It has a Borel subgroup, which is defined over the ground field. So quasi-split is a property when you're talking about group, not over an algebraically closed field. It has a maximal torus, which is defined over which is split over the ground field. Yeah. That's right. It's the same as saying that the minimal parabolic subgroup, which is something that always exists for a group over, say, a number field, a minimal parabolic subgroup. But in general, the minimal parabolic subgroup has a Levy component is non-abelian. And as you say, it's equivalent to saying the minimal parabolic subgroup is a Borel subgroup. Or is that what you said? Or another way to say it is it has an abelian Levy subgroup. That's right. That's right. You can construct, actually, there's a nice way to think of how you would construct all quasi-split groups, given split groups. Split groups we take for granted. They were constructed by Chevalier, and there's one for every, there's a simply connected Chevalier group, or I'm sorry, did I say quasi-split? Split groups, which is to say Chevalier groups. There's one for every, there's a simple Chevalier group, simply connected, for every Dickinson-Coxeter diagram. So one takes those as the basic objects. To get quasi-split groups, that's a little bit more general. What you do is you take a split group and you twist the Galois action on the split group. What does it mean to twist the Galois action? It means that you take a homomorphism. I'm not going to write, I won't write this down because I'll just say it. You can ask questions on what I say, but what you to get a general quasi-split group, you start with a split group. Those are the things that Chevalier gives you, and then you take a homomorphism from the Galois group. So given by, I'll put this in brackets. From the Galois group of the algebraic closure of F, this sounds worse than it is, into the group of outer automorphisms of G. Now, this always factors through a small Galois extension of F, and the outer automorphisms of G that you get are the automorphisms are isomorphic to the automorphisms of the diagram. So there aren't too many of those. GLN, you can flip the diagram. No, I guess you can do more. Yes, you can flip the diagram. That's just Z mod 2Z. Same thing with the even orthogonal groups. You can flip that. That's the type Dn. The Dickinson diagram has a fork at the end of it, and you can flip that. If you have a semi-simple group given by just a disjoint union of Dickinson diagrams, Coxeter Dickinson diagrams, you can permute them. Quasi-split groups come from outer automorph. So one can show that the outer automorphisms are precisely those that come from a group of automorphisms of the diagram. And there's a way to, given any automorphism of the diagram, there's a way to write down from that a canonical outer automorphism of the Chevalier group. First of all, you pick a Borel subgroup and you ask, outer automorphisms, remember, those are automorphisms that are defined, they're automorphisms that are defined modulo inner automorphisms. So for every outer automorphism, you can get a canonical description of it by first of all choosing. So in other words, an outer automorphism, what I'm clumsily trying to say, an outer automorphism is a coset in the group of all automorphisms modulo the inner automorphisms. Every outer automorphism has a canonical representation, not just as a coset, but actually as an automorphism. And what you do is you choose the automorphism modulo inner automorphisms that fix a given Borel that's using the definition that fix a given Borel subgroup of the split group. And that's not quite enough. You have to also pick a basis of the simple root vectors in the unipotent radical of that group. Now that's what's called by actually choosing a basis of the simple root vectors in the unipotent radical of the Borel subgroup. You can then further ask that the outer automorphism fix each of those root vectors. And that gives you a unique way to write down the outer automorphism. That is to say, it strips away the inner automorphisms that might be there, and you just actually get, from an outer automorphism, you get an actual automorphism of the group. That's relevant for this because, by the way, that's called, if you have a group, if let's say it's a quasi-split group, the choice of datum consisting of a Borel subgroup, and then on top of that, a basis of, or a basis of the simple root vectors in the unipotent radical, that's called a splitting of the split group. And that's what's needed in order to specify uniquely outer automorphisms acting on the group. Well, it turns out that that's very closely related to the Langlands construction of the dual group. And if in fact you have an outer automorphism of the group given by this splitting, that you can construct an outer automorphism of the dual group. I don't know if I've said this very well, but the point is that a quasi-split group comes with some extra data. It comes with an action, not just of these it comes with an action not just of the Galois. So what it comes with, so here we have a homomorphism of this Galois group into here that factors through a very small Galois extension into here. And so it comes with the similar action of Galois group of F bar over F on the dual group. And it's given by exactly the same set of data that you have to fix in order to get this action. And by the way, this action, this homomorphism of the Galois group into the actual group, an actual, not just the quotient group, which is how outer automorphisms are defined, not just the quotient group of automorphisms modulo inner automorphisms, but an actual group of outer automorphisms as automorphisms. What you do is you use that homomorphism to twist, to change the Galois action on G F bar that comes with a split group. A split group is a group defined over F, the smaller group, but it, of course, if you were to take F bar, it has a Chevalley group has an action of the Galois group on G over F bar, and it's the fixed points of that action that gives the group of F points of the Chevalley group. Well, a quasi-split group comes from taking a split group and taking its points in G F bar and changing the Galois action of the group on that G F bar. You take the one that's given to you canonically as a Chevalley group and you twist it. In other words, you compose it with this Galois action, this homomorphism of the Galois group into the group of outer automorphisms. And so that gives you a new Galois action of G of the Galois group on G of the group of points in GF bar, and its group of fixed points is the group of F points, the quasi-split group. that's how you construct it. I haven't said it, I think, all that clearly, but it might take a lecture to explain it precisely, and it's a really very simple concept. I think the first article by Springer, actually, in the Corvallis proceedings is quite good, and it tells you how you get these things, what a splitting is, a Borel subgroup with a basis of the simple root vectors in the unipotent radical, and so on. And I think he explains this stuff. But you also get, just by the construction of the dual group, so it comes with an action of the Galois group on G hat. G hat is already a complex group, so we're not changing any Galois action on that group. That's a complex group. But nonetheless, it gives a mapping of the Galois group, but really a much smaller one here, K, often like just a quadratic extension, has automorphisms of this complex group. So it's an action of this discrete group on G hat by complex outer automorphisms. So the bottom line is you use this to construct a slightly bigger complex group, a disconnected complex group, to define what is now called the L group of G. And it's now written as G upper left upper L, and it is the group G hat, the connected complex group, coming from the dual group of the Chevalley group, but the semi-direct product of that by this group of automorphisms. I can write it either as the Galois group of F bar over F, but that looks very forbidding. The point is that up to a finite Galois extension that's usually very small, the resulting this acts trivially on this and can be ignored. So let's just say, or better, or more concretely, GL is equal to the dual group with an action of the Galois group of K over F for some finite Galois extension K over F. Now, to represent the quasi-split group, you don't have to, as I say, you don't have to take K to be very large. It's usually just some small Galois extension of F. It could get large if you have a semi-simple group whose diagram is a disjoint union of a whole lot of connected diagrams, but and then you might have to choose K to be rather large. But in any case, what we do and what Langlands did in his paper for some finite field extension K over F. And he left that open. He didn't say, nowadays you often write it just like this, but Langlands left it open, and he just said just K over F is sufficiently large, but a little bit misleading terminology. Sufficiently large means it's large enough to include the group that you really do need to define the action of the action on G hat. You often choose something larger, and in particular, rather than to make the whole picture look uniform, to treat arbitrary quasi-split groups, you allow yourself to choose any finite Galois extension K over F that's sufficiently large. And in particular, you allow yourself to choose an extension, the Galois group of an extension K over F, even in the split case. So in particular, if G is split, so to make this uniform for the sub collection of split groups within the quasi-split groups, you could define the L group to be simply the dual group, which is what we had been taking. And well, now you have, if it's a split group, now this Galois group acts trivially on here. And so you don't take the semi-direct product, you can just take the direct product of the Galois group of K over F. And so this is just for some extension that you leave open. You could take it all, the only condition is that it's sufficiently large that it includes the Galois action on the Galois group on G hat in the case, that is to say, K is a little, is an extension over of F that you have to take to include this action on G hat. So I guess you could say you could take GL to be this for some sufficiently large, in the sense this isn't really too large, but sufficiently large Galois extension. K over F. Okay, does that make sense? Any questions? Yes.
You're saying, so if you have a split group, this comes with a homomorphism from the Galois group into the automorphic. This is by Chevalet's description?
No, Chevalet didn't talk about that at all. The person that did that was follow-up. It was Steinberg. Chevalet constructed all what are known as split groups. It was Steinberg who wrote then a paper, Variations on a Theme of Chevalet. And he said you can construct, the word quasi-split didn't exist in those days, but he described how you'd get all quasi-split groups from what Chevalet had done. And in particular, you choose a group of outer automorphisms of a Chevalet group.
So you get from here action on G. So you, for a quasi-split group, you get action of the Galois group on the
by outer automorphisms.
On the dual group.
You get it by an action, first of all, on the group itself, and you use that to twist the Galois action. And then you also get it. It just hands to you also the same action defined in the same way on the dual group. But there, it's literally an action of outer automorphisms on a complex group. Yes, it's all. No, it's just by definition. It's a definition. The outer automorphisms, in the sense of the quotient of the group of all automorphisms modulo inner automorphisms, is very small. And that's what's happening. You're using automorphisms, you can identify it with automorphisms of the Coxeter-Dinkin diagram that comes with the Chevalet group. Is that what you were going to ask? Yes.
I wanted to ask, if you take G to be GLN over this group,
yes.
Then what can you take the extension over?
That's how you get unitary groups. That's how you get unitary groups. So it's typically it is at most it's a cyclic extension of order n. what are the automorphisms of the diagram? They're just two, actually. They're just two. Getting confused. So it's just a group of order 2, and it's the automorphisms of the diagram for AN, which is just n vertices all joined, and you can flip that. That's the only automorphism of it. And that gives you unitary groups, which are certain unitary groups, which are quasi-split groups. Was that what you were going to say? Yeah. Yes. Pardon me? It's a semi-direct that is with the image of the multiple of T. That's right. It's a group. So you, because by choosing what's known as technically as a splitting, as I have described, you get from the group of all outer automorphisms regarded as a quotient of the group of automorphisms, as a coset within the group of all automorphisms of the group, you actually get a group of automorphisms of the group itself. You get so you have one, you have the group of inner automorphisms of G, you have the group of all automorphisms of G, and then you have the quotient, and this, I guess, is what's often written as outer automorphisms of G equals the automorphisms of G modulo inner automorphisms of G, and 1. And so this is all quite pretty trivial in this situation. So this is a quotient of this, and it's the quotient given. The quotient is given by automorphisms of the diagram. Does that make sense? Okay. Well, after all that, we're going to take so G over F, a number field, quasi-split. Okay, so then we've got GL, the semi-direct product of this connected complex group with Galois K over F for some large, sufficiently large extension K of F. This is how Langlands has set it up. And all right, so everything that I've said carries over to this situation. In particular, the notion of an automorphic representation is an automorphic representation of GA. Well, first of all, the theorem of Flath says that I mentioned last time, I think, that it breaks into a restricted direct product of representations over the local field. And you have the notion of a representation IV being unramified. And so IV is unramified if the quasi-split group G, but now taken if the quasi-split group G, now regarded as a group over the completion, the local field, is unramified. So you ask that that group be unramified, and you have to define what you mean by this to be unramified. So definition. A group a group, let's say a reductive group, G over FV is unramified if, well, first of all, if it is quasi-split, okay, so quasi-split is automatic for each of these local constituents, but also it is it's quasi-split and split. That is to say, we're talking about now what you have to take for the Galois extension over which the group becomes split. And the condition for it to be unramified is it's split over an unramified extension. Let's say EV FV of FV. So in general, you're going to, given a quasi-split group, you've got this extension of fields over which the group is split. So given a quasi-split group, you've got an extension over which it's split. And we would say that a group over FV is unramified if not only is it split over some extension, but if it's split over an unramified extension. And so it's easy to, it follows almost from the definitions. Almost all, for almost all. V, G over FV is unramified. And this means that G in particular G hat over FV is equal to the semi-direct product of G hat with a field extension, Galois, the Galois group of an unramified extension KV over FV, or in particular, the group generated by a Frobenius class. So this is unramified Galois group, an unramified Galois group of FV. Okay, so the assertion of functoriality from before generalizes um, um, as before, from before. I guess there's something I have to also say here. Um, 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 so I need to insert it here. Um, if pi v is unramified, we ask that it generalizes for pi v is so I'm sorry to say that G over V is unramified, we ask first that the group G over FV is unramified in this sense. It's split over an unramified Galois extension. And by definition, one gets. So I haven't if it's unramified, we ask, so the for G over V to be unramified, we ask that the group G over FV be unramified in this sense. And pi V is unramified in the sense that pi V restricted to KV for a suitable maximal compact subgroup contains the trivial one-dimensional representation. And when this is so, the things that I mentioned in the case of a split group all have immediate extensions to the quasi-split group, and in particular to the places V that are unramified in this sense, namely G splits over an unramified extension of FV, and if the restriction of pi V to KV for a suitable maximal compact subgroup contains the trivial representation. Now there's one actually condition that you have to put, well, I'm not going to say, but there's for p-adic groups, maximal compact subgroups are not all conjugate the way they are for real groups. But there's the notion of a special maximal compact subgroup, and those are not all conjugate either, but I'm just going to say a suitable maximal compact subgroup contains the trivial one-dimensional representation.
So in the old case, the suitable one was G of Z.
Well, I was talking about GLN, And so I just took G of ZP.
Okay.
So that's
PLN, then you take ZP is the suitable one.
Is the suitable one. And that doesn't, yes, that's right. Now, for a general split group, you have to take what's called a special maximal compact. There are maximal compact subgroups that don't have that property. And for a quasi-split group, you have to take one that's called hyperspecial.
Does Steinberg have some of this in the dark?
No, he didn't. I don't think so. He didn't talk about this. This is all stuff that has grown out of Langlands' paper.
So can you not serve it or Langlands paper in Corvallis?
No, his paper for Bachner. He talked about suitable. He didn't talk about special. The notion, I think I'm right in saying that the notion of a special maximal compact subgroup probably wasn't around when Langlands wrote his paper. Somebody can perhaps correct me, but I think it wasn't around. It was the notion of a special maximal compact subgroup was, I guess, it arose from the work of Bruja and Titz on buildings for p-adic groups, and also the notion of a hyperspecial maximal compact subgroup, which is a slight further restriction in the case of a quasi-split p-adic group. So if you don't mind, I'm just going to say for a suitable maximal compact subgroup contains the trivial one-dimensional representation, and then in this case, we have a semi-simple conjugacy class, pi v. Pi v is unramified in this sense. We get pi c pi v, or cv of pi. And this is a semi-simple conjugacy class. Conjugacy class in GL. So now we're talking about not just a connected complex group, we're talking about G hat, semi-direct product with the Galois group. And in this case, it would be the Galois group of, it would be the Galois group of F, V, the unramified, Galois group of KV over FV, where this is an unramified extension. And the semi-simple conjugacy class is the product of a semi-simple conjugacy class in G hat and its image in here. So let's say whose image so CV is just a little bit more general. It's not just a conjugacy class in this connected complex group, but it's a conjugacy class in this disconnected complex group, whose image in this Galois group, in the Galois group of KV over FV. So this is an unramified Galois extension, is equal to the Frobenius element, the generator of this group. So I guess we could call that Frobenius. The group, the Frobenius element that generates the unramified Galois extension. Okay, so I want to leave this here.
What was the last statement over there? How does that?
So I'm not proving it, but I'm saying that what we discussed earlier for split groups, or really for GLN, where at almost all places an automorphic representation gives you a semi-simple conjugacy class in GLNC, what happens here is for an automorphic representation of the quasi-split group, for almost all places, you get a semi-simple conjugacy class, not in G hat, but rather the bigger group, the semi-direct product of G hat with this group. And it has the further property that the projection of this conjugacy class, this is an unramified Galois extension, a finite unramified extension of FV, and its Galois group then is a cyclic group generated by the Frobenius element. And the property that arises then in this case is that it's a semi-simple conjugacy class in this L group whose image in here is the Frobenius class, the generator of this Galois group. Is that
Over there, like in the last sentence, you write whose image in the L group. So over there, I see image.
it's whose image in here, this Galois, this unramified extension, is the Frobenius class. That is to say, the canonical element that generates that Galois group. Question? Further questions? Okay, and then finally, the assertion of functoriality. I'm sorry, this had to go in here. When I gave this lecture, I gave this as a colloquium some time ago, and I didn't put all of this stuff in, but I realize that's, so I didn't write it out, but I realized it probably wouldn't make much sense if I didn't write it out here. Langland, this is all in Langland's article, but it's tenuous because a lot of this stuff hadn't been done. And so he just said that this is what's going to happen, but it hasn't really, we're going to assume that this is what happens, although it has to really be done. Anyway, the assertion, I'll just add that the assertion of functoriality from before then generalizes to the case of the quasi-split group G over F as follows. If rho prime, okay, so you remember, we remember what functoriality said. It said that if you have two different, I don't remember if we said two different general linear groups or whether we said two different split groups, but the condition of functoriality was that if you had a homomorphism from the dual group of G prime into the dual group of G, two connected complex groups, and if you had an automorphic representation pi prime of the first one, then there was an automorphic representation of the second one such that the conjugacy classes, the CP primes attached to the first, the automorphic representation of the first group, G prime, the smaller group, let's say, that the automorphic representation of the bigger group had the property that its CPs are the image of the ones that were attached to the original group. So let's say the assertion of functoriality as before generalizes. And so it really, I have to say, it really is important to treat this slightly larger situation of quasi-split groups. And but it generalizes, let's say, in the obvious way. if rho prime, so rho prime, we had it before, it was a homomorphism of the first, don't write this down. It was a homomorphism from the first complex group to the second one. Yes, you can write this down. But now we're talking about the L group. So it's from the L group G prime of G prime, which is the semi-direct product of G hat prime with the Galois group. And remember, we're taking K to be any sufficiently large Galois extension. And so in particular, I would take it large enough to work for both G prime, the quasi-split group, and G. So this would be then, by choosing K sufficiently large, this would be from the L group of G, namely G hat, the Galois group of K over F. Okay, so it's a homomorphism from this L group to this L group, this being a semi-direct product of G hat with the same Galois group. We choose K large enough to work for them both, but there's one further condition. If L is what's called, these days, Langlands didn't use this terminology, is what's called an L homomorphism. Namely, the diagram, it commutes with the two projections of these semi-direct products onto the Galois group. The diagram, so you have G prime, GL prime, a homomorphism from that into GL, and both of these things project onto the Galois group of K over F, and you ask that this commute with the projections onto the Galois group. So that's what you require of the homomorphism rho prime. So this is called, what's I guess called an L homomorphism. It has to commute with the projections onto this group. And then I guess I can write it out next time, but then it has the property, exactly the same property, that for an automorph, that this is just for any L homomorphism from one to the other, but then you say if you have an automorphic representation pi prime of the first group, there's going to be an automorphic representation pi of the second group, such that the conjugacy classes, the family of conjugacy classes defined almost everywhere for the first group by, according to this property, map to the conjugacy classes defined for almost all P in the second group. Just the same assertion. Is that, I don't know if by writing this out from, some of this out from memory, I'm not sure I made it as clear as I could have.
Does it make sense to talk about automorphic representations of L groups?
The physicists and the geometric Langlands people do that, but Langlands gets, are we off the air now? Langlands doesn't like that. He said, look, you've got they're two different objects altogether. You've got one, a group over F, and secondly, you have a kind of a dual group, but it's over the complex numbers. It's supposed to be the group that keeps the parameter, that stores the parameters of the representations. The physicists and I think the geometric Langlands people do have duality, and they. I think there's something happening there, but it's not part, at least, of this early part of the Langlands program. But it's a reasonable question to. But then you have to choose a rational structure of the dual group, not just a complex group. And then how do the parameters, the complex group is the storehouse of the parameters of representations. I mean, parameters of representations have always been sort of complex things, like in Fourier transforms and Fourier series. The dual group or the L group is the storage facility for the parameters of automorphic representation. The conjugacy classes, that's right. And also, yeah, well, that's sort of the main thing. But next week, or maybe on Friday, I will start talking about the remainder of Langlands' article, in which he proposed parametrizing all representations of the p-adic groups, of the completions, by homomorphisms of the Galois group, or something bigger called the Bay group, into the L group. And so they're not just the conjugacy classes, but also the parameters for that classify the representations at the other places as well, in particular at the real place. So we'll talk about that. Maybe Friday. I'll just finish this up, and then we'll talk about it. This has this sort of right at the functoriality conjecture, the way we've set it up now. Suddenly something happens because you set it up in this way, and it's non-abelian class field theory. It just comes out of this, so we'll describe that next time.
The statement over here is that X rho prime is an L homomorphism.
Oh, I'm sorry. I've been writing this as rho prime. Sorry. Yes.
The statement is that if it is an L homomorphism, then you get that functoriality in the previous set.
That's right. That's right. So in other words, an axiom that you require in this more general situation for rho is that it be an L homomorphism. It works. To make it work, that's what you have to ask of rho in the case of quasi-split groups.
Whereas previously, what conditions do we have on rho?
Rho was just a homomorphism of a connected complex group into another connected complex group.
Right, it was just a homomorphism of the dual groups.
Of the dual groups. And here it's a little bit more, not much more. The main part of it is still what it does on the subgroup, on the dual groups that are subgroups of these, but then there's this additional thing that happens on the semi-direct product. Yes.
So again, the last time the big example was when we used Jacquet-Goldbach to
Yes.
say that, look, you have analytic continuation and everything, if you can prove.
That's
So,
right.
Something like that can also be said here.
Oh, absolutely. So next time we'll do 4 examples. That's the first example. The same example that worked for split groups. We'll call that example 1. And once again, the definition of automorphic L functions carries over right away to this situation. And then so that example carries over as well. But then there were 3 other examples that Langlands put at the end of his paper, which some have only hinted at. But so we'll do those spectacular things. The second one is non-abelian class field theory. And third one is Ramanujan's conjecture. Yeah, well, it was just, just threw them out and people didn't, yeah. I'm not going to go into any detail on those things, but just. Pardon me, yeah.